Free response number 2 wants you to find the Taylor series expansion centered at c equals 7 for the given function's square root of 9 plus x. So when they give you a Taylor series, the first thing that you usually want to do is you want to make your chart. So the columns of those chart is n. You want an fn of x column, and you want an fn of a column. So what I'm going to do is I'm going to start at 0. I'll do 1, 2, and I'll do 3. I'll also write 4 in there too. 4 or 5 Taylor series terms are usually enough to figure out what the pattern is. So you just want to make sure that you include enough. Don't stop at just like 1. Make sure you expand out enough terms to know exactly what the series is doing. So at fn of x at n equals 0, that's the original function itself. So I'm going to go ahead and I'm actually going to write it as 9 plus x to the 1/2, which is the same way as writing square root of 9 plus x, except now I'm just going to write it as its power form. So 9 plus x to the 1/2. And if I go ahead and I evaluate that at c equals 7, so in this case I'll actually make this a equals 7 because the notation that Dr. Chewy uses is also a. So fn of 7 in this case is what I'm looking for. I would end up with 16 to the 1/2, which is equal to 4. Okay, cool. Now when I plug in n equals 1, I want to take the derivative, so n equals 1 corresponds to the first derivative. Take the derivative of this, I end up with 1/2 9 plus x to the negative 1/2. Okay? And I can also evaluate that at a equals 7. So when I plug that in, I end up getting 1 over 2 square root of 16 on the bottom. So I end up getting 1 over 2 times 4. So I'll actually just go ahead and write it as 1/2 times 1/4. Again, when you're writing out these Taylor series coefficients, you want to make sure that you simplify as least as possible, because sometimes if you try simplifying stuff, you might end up losing out on terms that could show patterns when you actually expand out the Taylor series. So I want to write it like this because, again, I want to account for every single term, and I want to make sure that I'm not missing out on any kind of hidden pattern or anything. So leaving it like this should be okay. N equals 2, I can go ahead and take the derivative of this term. When I derive that out, I end up with 1/2. And again, trying not to simplify anything, I'm going to multiply by a negative 1/2 in front. That causes this to be 9 plus x to the negative 3 over 2. And also keep in mind that normally we would have to take into account chain rule, but the derivative of the inside is 1, so we're just technically multiplying by 1 every single time. So when I go ahead and plug this in, I end up getting 1/2, negative 1/2. I end up getting 9 plus 7 to the negative 3 over 2, so that's 1 over 16 to the 3 over 2, which would be 1 over 4 cubed. So I'm just going to go ahead and I'm going to rewrite this as 1 over 4 cubed. Okay, good. So I do already kind of see a pattern emerging. I see a 1/4 and I see a 1/4 cubed. Now there wasn't a term here, but that's okay, because remember, if the term doesn't fit in the pattern exactly, we can always just add it to the front and move the index forward 1. So if we have to leave that term out, it's not the end of the world. So I do kind of see a pattern emerging, but let's keep going, because again, 2 terms is not enough to really tell a pattern. We really have to get a good overall view of the series before we can declare that there's a pattern here. So the next term would be 1/2 times negative 1/2 times negative 3 over 2 times 9 plus x to the negative 5 over 2. Okay, well at least the derivatives are easy to take. So that we have that working in our favor. So now I end up getting 1/2, negative 1/2, negative 3 over 2. And when I go to plug this in, I end up getting 1 over 16 to the 5 over 2. So I end up getting 4 to the 5th. Make sure you go through the algebra and simplify it just to make sure. But 1 over 4 to the 5th should reduce down from 1 over 16 to the 5 over 2. So, again, looks like we were right about the pattern here. Definitely looks like there's some kind of term emerging here. But let's keep going. Let's do one more term just to be sure. So I have a 1/2, I have a negative 1/2, I have a negative 3 over 2, I have a negative 5 over 2, and the next derivative of this would be 9 plus x to the negative 7 over 2. So when I go ahead and I write that out, I end up with 1/2 times negative 1/2 times negative 3 over 2 times negative 5 over 2 times 1 over 4 to the 7th. And again, that comes from plugging in a equals 7. I get 16 to the negative 7 over 2, which is 1 over 16 to the 7 over 2. And if I break that down a little bit, I can turn that into 1 over 4 to the 7th. So, good. Now, we have a decent amount of terms. I think we don't need to expand anything further than here, because I definitely do see some patterns emerging. It looks like we have a little bit of an alternating series here. And it looks like there's also just 2's on the bottom. So what I'm probably going to end up doing is I'm probably going to end up turning this 4 into a 2 as well. Again, I want everything to match as much as possible. So I don't want to leave extra 2's and 4's all over the place. I want my series to be as condensed as possible. Now, on a free response, it might be okay if you don't condense everything down to exactly how they want it. Again, they know what answer they're looking for. So just make sure that you do account for every term and that you at least write it out in its end form if you can. So what I'm going to do is now I'm going to write out my Taylor series coefficients. So remember, the formula for a Taylor series is f of x is equal to the summation n equals 0 to infinity fn of a, where fn of a are the terms that we just solved for, so we have those, x minus a to the n, which we can find because we know what a is, and n factorial, which we can just write out. So now let's take a second and let's expand out these terms. So f of x is equal to, so if I want my n equals 0 term, so I have my fn of a, that's 4 times x minus 7 to the 0, which is 1, but I will denote it as x minus 7 to the 0 because, again, I think it's good notation to make sure that you do account for that extra 0 term. So, 0 factorial, which also, as a review, 0 factorial is equal to 1. 0 factorial is not equal to 0. If it was equal to 0, we'd have a huge problem here. But 0 factorial is equal to 1. Now, our next term is going to be 1/2, 1/4. So we have 1/2, we have 1/4, we have times x minus 7, and this is to a first power divided by 1 factorial. Good. So we have 2 terms so far. Let's keep going. So now I have a negative term here. So I have a 1/2 times a 1/2, 1 over 4 cubed. Then I also have my x minus 7 quantity squared, all divided by 2 factorial. And again, I'm not really going to move anything around or simplify anything. I want to get the pattern first before I do anything. So, 2 factorial here. Now we move down to our n equals 3 term. So when we write out our n equals 3 term, we end up getting, and I'm going to try to not run out of room here, so negative times negative is a positive. So I end up getting positive 1/2, 1/2, 3 over 2, 1 over 4 to the 5th, x minus 7 cubed over 3 factorial. Sorry, that is a factorial. Now we have our last term. Our last term is going to be a negative. So minus 1/2, 1/2, 3 halves, 5 halves, 1 over 4 to the 7th, x minus 7 to the 4th, all divided by 4 factorial. And keep in mind that this is not the only terms in our Taylor series There are more terms over here, so I'm just going to write a plus ... to denote that these are only the first 5 terms in this case, and that there are more terms, but again, we don't need to write out every single term. It's actually impossible to write out every single term because it goes to infinity. So we want to write out enough terms so that we can get a good feel for what the series is going to do. Now that we have those terms, let's see if we can find our infinite series representation of it, because that's what we're looking for in this case. That's the most important thing. I'm going to go ahead and erase our chart here. So we have f of x is equal to all these numbers. So now what we need to do is now we need to kind of look for patterns. So when I'm looking for a pattern, I'm going to write n equals 0 to infinity. So I notice right away that obviously it follows x minus 7 to the n over n factorial. So I'm going to go ahead and just denote that in here. Those are the easy ones. In this case, there's no sign that the factorial is really dropping out. And even if there is, if it does drop out somehow, we should be able to find a term that will cancel it out in this representation. So I'm not going to cancel it out until I'm absolutely sure it's going to cancel out. Now we need to solve for the other terms. So one of the things I notice is that there's a 1/2, there's a 1/2, 1/2, then a 1/4 cubed, 1/2, 1/2, 3/2. So it looks like every single time it's like 1/2 to like an n power. So I'm going to write it as, I'm going to extend this little denominator over, and I'm going to write it as 2 to the n on the bottom. Okay? So that at least accounts for these 1/2 terms that are kind of showing up all over the place. But now we kind of run into an issue. So we have this 1/4, I have 1/4 cubed, 1/4 to the 5th, 1/4 to the 7th. So I could also denote this as 4 to the 2n plus 1. So I could write this as 4 to the 2n plus 1 on the bottom as well. Sorry, I'm going to write that a little bit bigger, just to make sure. So 4 to the 2n plus 1, n factorial. And that does fit this pattern, right? It even fits it right here. Well, actually, no, it doesn't fit it right here now that we look at it, because there's also no way to account for this 4. So it looks like immediately we're going to have to leave this first term completely out of our series, which is okay. Again, you can totally do that. You just have to make sure that you write that off to the side and change the index accordingly. So what I'm going to do is I'm going to go ahead and make a statement that says we're not going to include this term right here, which if we go ahead and simplify it, is just 4. So I'm going to change my index to n equals 1, and I'm going to say that my new series is equal to 4 plus my series. So we've already gone ahead, we've basically eliminated this term from the pattern. So now this should fit every single term so far, from at least what we've gotten. Again, there's still a few more terms that we have to take into account, but so far it looks like it does take it into account pretty well. 4 cubed, 4 to the 5th, 4 to the 7th, but not at n equals 1. So it looks like maybe this isn't really working out that well. So maybe we should eliminate this term and we'll come back to it. Again, by getting rid of this 2n plus 1, it kind of threw everything off a little bit. So let's see if we can come back to that. Now, the one thing I do notice is that there is a negative, a positive, and a negative. So we can go ahead and account for that really quickly. That looks like it's just going to be like a -1 to the n. But it's kind of weird because in this case it doesn't really fit right here. So it might have to be -1 to the n plus 1. Okay. Well, I guess that does take into account here. So if this was n equals 1, that would make it positive. If it was n equals 2, it would make it negative, positive, negative. Okay. Looks like we're kind of working through it so far. Again, this stuff is difficult, so it does take some time to work through. And in this case, there are a lot of numbers that we do have to take into account, so we want to be really careful when we're going through. Again, we only want to cancel out stuff when we're completely sure it cancels out. So we have -1 to the n, x minus 7 to the n, 2 to the n, n factorial. So now we have to do something about these 4s. And again, these 4s are not really working out that well. So what I'm going to do, I'm basically going to say that 1/4 is equal to 1/2 squared. I'm going to say that this is equal to 1/4 to the 6th. So again, what I can do is I can say that if I have a 4th, that's basically equal to 1/2 to the 2. If I have a 1/4 cubed, I can say that's 1/2 to the 2 quantity cubed. And when I take a power to another power, I end up getting 2 to the 6th. So it looks like there's a lot of extra terms in here, but what it looks like we can do is maybe we can just modify this 2 to the n somehow to account for those terms. So our first term in this case is, that would be 1/2 cubed. So we would have total, we would have a 1/2 cubed. Okay. Here, if I did the same thing, I would end up with a 1/2 to the 8. Well, that's a really, really big jump. That went from 3 to 8, so this is now going to become 1/2 to the 8. Here, if we try to do it, 4 to the 5th is 2 to the, so that would be 2 to the 2 to the 5, so that would be 2 to the 10, 11, 12, 13, so that's going to 13. So I do have this extra 3 here, and I'm not going to get rid of that. I'm just going to write it as a 3 off to the side, and I have 1/2 to the 13. Okay, so it looks like it's jumping by pretty big gaps in this case. And I'm not entirely sure how that's going to evolve, but let's see if we can figure out a pattern. So I'm going from 3 to 8 to 13. It looks like there's a gap of 5 in between. Okay, so if there's a gap of 5 in between, that would tell me that if I'm at n equals 1 and I need to get to 3, well, let's see, 5n minus 2 should satisfy that. So if I have n equals 1, 5 minus 2 would be equal to 3. Okay, that works. If I plug in n equals 2, I'd want 10 minus 2, which is equal to 8. Okay, that works. Okay, so n equals 3, that would be 15 minus 2, that's 13. Okay, yeah, so I think that's actually working in that case. So one of the most important things that you have to do is, when you're looking at the patterns, think of how you could get like an even and odd number, and then think how I could get from that even and odd number to the number I want. So in this case, it's 3, 8, 13, which doesn't look like it's any real pattern, right? It's not like they're not prime numbers or anything. Well, sorry, a couple of them are prime numbers, but 8's not a prime number. So if there's not really an apparent pattern, think of something close to it. So if I was going by like odd numbers, how can I go from this series to that? And that's kind of the key of these Taylor series approximations. So now that I kind of know that, what I'm going to do is I'm going to rewrite this 2 as a 5n minus 2. So now that should account for all of my coefficients with the 2's. So that's good. And that also accounts for here too. If I have 4 to the 7, that's 2 to the 14, 15, 16, 17, 18. So the next term in here would be 18, which if I had 20, so at n equals 4, 20 minus 2 is equal to 18. So it does fit. So that's good. So we were able to figure out 2 to the 5n minus 2 was our pattern in this case. Okay. Now, there's one more term that we need to take into account, and it's this 3. So here, there's no additional term. There was a 4 here, but again, we're already excluding that from our series, so we're just going to ignore that. Now we would have like a 1 coefficient here, a 1 coefficient here, a 3 coefficient here, and now we have a 1, 3, 5 coefficient. And I guarantee the next term would probably be 1, 3, 5, 7. So what do we do? Well, 1, 3, 5, 7, it's as if all those odd numbers are multiplied by each other. So what that tells me is that it's probably going to be one of those weird ones, the 1, the 3, the 5, And then when we get all the way to the very end, it'd be like a 2n minus 1 or something like that. So it'd be one of those terms where all the numbers are being multiplied together up to the end value that you want. So if it was at n equals 3, it would be like 1 times 3 times 5. Or if it was n equals 4, 1 times 3 times 5 times 7. But there's a problem. This term doesn't fit that formula. It fits everything else just fine, just not this one. So how do we take that into account? Well, if it doesn't fit the pattern, again, we'll just exclude it. So what I'm going to do is, in addition to excluding this term, I'm just going to leave this term out as well. Because if it doesn't fit the pattern, there's no way that you can fight with it and try to get it to. You can sit there all day, and it may or may not fit the actual pattern. So what I'm going to do is I'm just going to say that in addition to this 4, I'm going to add my n equals 1 term as well. So what I'm going to do is I'm going to go ahead and just kind of rewrite my entire series. I'm going to say that the new one should be 4 plus, I have x minus 7 times 1 over 8, so x minus 7 over 8 times 1 factorial, that's just equal to 1, so we don't need to worry about that. Plus my series, now indexed at n equals 2 to infinity, of negative 1 to the n. So before it was negative 1 to the n plus 1, but now, if this term is going to be negative, if I plug in n equals 2, that doesn't work anymore. So I need to plug in n plus 1. Oh, that was what it was. Never mind. Negative 1 to the n plus 1 was what it was. Okay, so that's okay for that term. So now we have this x minus 7 to the n, which actually I'm going to write on the other side because it's good notation to write the x minus a to the n term on the complete outside. That's usually where it is in the Taylor series. So what I'm going to do is I'm going to write this 1 times 3 times 5 to the 2n minus 1 term outside. And let's see if that actually fits. So if we start at n equals 1, I have a 1 term, okay. I start at if I go to my n equals 3 term, I have 1 times 3, okay, that's good. If I go to my n equals 4 term, I have 1 times 3 times 5, okay, that's good. So it looks like that should fit in this case. And let's see if it actually fits with the 2n minus 1. So if I plug in n equals 2, I should get 1. But I actually don't in this case. So if I plug in n equals 2, I end up getting 3. So that would insinuate that this starts at 3 instead of 1. But I want it to start at 1 because I know that this term has a coefficient of 1 that I need to match to get it to fit this series. So what I'm actually going to do is I'm going to write this as 2n minus 3. Now, at n equals 2, that should fit that because 4 minus 3 is 1. At n equals 3, 6 minus 3 is equal to 3. N equals 4, 8 minus 3 is equal to 5. So now 1 times 3 times 5, 2n minus 3 fits that series perfectly. On the bottom here, we have our 2 to the 5n minus 2. And we also have this n factorial term. So now, question is, if we go back through and compare the terms in this series to the terms we had here, do they match? In fact, they actually do. So after all this work, we have found the Taylor series representation for this term. And actually, I almost forgot. Don't forget, x minus 7 to the n. And this doesn't need to be changed at all, because remember, this still corresponds to the squared term, this still corresponds to the cubed term. Same thing with the factorial. We didn't change the factorial at all because the first terms were just 0 factorial and 1 factorial. So they're not there because, well, they just don't show up at all. They're just dividing by 1. So those terms don't need to be changed. But for now, we have found the Taylor series representation for f of x equals square root of 9 plus x at a equals 7. Good. Now, there's one more part to this question, and that is a bonus 2-point question at the bottom. Now, the only way you can answer that question is if you know the Taylor series representation. So, if you weren't able to figure out number 2, you probably wouldn't have even attempted the bonus question. But let's go ahead and let's see if we can answer that question. So I'm just going to make myself some room here so we can write that down. So for this bonus question, it says use the second order approximation to approximate square root of 16.06. Leave your answer in 3 terms. No need to simplify. So a second degree Taylor polynomial corresponds to when the series reaches n equals 2. So what that means is I want to expand out my Taylor series until I get to my n equals 2 term. So that tells me that if I know my Taylor series expansion, which is equal to this whole thing right here, I can go ahead and I can write out my Taylor series approximation. So f of x is equal to 4 plus x minus 7 over 8 plus, at n equals 2, I need to write out what that term is. So I would end up with negative 1 x minus 7 squared over, if I plug in n equals 2, I end up with 10 minus 2, that's equal to 8, 2 to the 8 rather, and 2 factorial. And I'm just going to leave it like that because again it doesn't say that we need to simplify anything, it just says that we need to write it out. Okay, now there's one more thing I need to solve for. I need to figure out what x value I'm going to plug into, because what you're actually doing now is this is the application for the Taylor series. You are going to approximate square root of 16.06. So this is the value that it wants you to approximate using this Taylor series expansion. So what that means is that I need a constant. But first off, what I need to figure out is I need to figure out what x value I'm going to plug into this equation. I'm not plugging in square root of 16.06 because the function that it was based off of was square root of 9 plus x. So because of that, I need to figure out what x value will give me square root of 16.06. That's the x value that I want to plug in. So when I go through and try to solve this, if I square both sides, 16.06 is equal to 9 plus x. If I subtract off 9, that tells me that my x value that I want to plug in is 7.06. This value, when plugged into here, will give me an approximation of square root of 16.06. So when I go ahead and do that, f of 7.06 is equal to 4 plus 7.06 minus 7, that's 0.06 divided by 8, minus 0.06 quantity squared over 2 to the 8 times 2 factorial. This is a constant value, and it matches exactly what I have on my sheet here, except the only thing that you could do is this 2 factorial. Because 2 factorial is just 2, you can factor it into here. So 2 to the 8 times 2 is just 2 to the 9. And from there, you're good. So this would be the answer to that bonus question. All you're doing is you need to figure out what x value you need to plug into your second order Taylor approximation. Remember, second order means that you want to expand it until you get to the n equals 2 term. So in this case, my second order Taylor approximation has 3 terms. It's not just the n equals 2 term, it's the 3 terms that lead up to n equals 2.
The Teaching Center, UF's Learning Resource Center.